Hello everyone, I'm Xuefei from Tsinghua University. Happy to share our NeurIPS 24 work, Can LLMs Learn by Teaching for Better Reasoning, a preliminary study. I'll first give an overview on our work. In recent years, we have been impressed by LLMs with extensive knowledge, strong planning skills, and good intuitions. However, the ability of current LLMs to provide accurate knowledge and reasoning appears to lag behind these other abilities. Actually, some of the difficulties in accurate reasoning mirror some difficulties encountered in human learning. Therefore, we wonder whether integrating human educational strategies or concepts may help improve the reasoning ability of LLMs. In human learning, the learning by teaching method, abbreviated as the LBT method, has been shown to promote accurate knowledge building and reasoning. We know that during the teaching process, not only are the students improving, but the teacher itself can also benefit from explaining knowledge to the students and receive their feedback. This paradigm or concept is different from the learning from teacher paradigm, which is widely explored in machine learning, such as we can let a model learn from human teachers' annotations, or we can let a small model learn from a stronger model by knowledge distillation. Before conducting the exploration, we first ask that in human education, how and why LBT improves the teacher's abilities. We summarize three major ways in which LBT is helpful. The first one is the increased self-accountability or self-motivation, which our work actually didn't really focus on. The second one is the explicit articulation of implicit and vague thoughts. During the preparation of the teaching materials, the teacher needs to use clear and organized language to convey its inner thoughts out to the students. Note that here we write down an LBT teaching material quality assumption, LBT TMQ assumption here. This assumption reasonably assumes that teaching materials that make it easier for the students to learn have clearer and more accurate logic. This provides us a way to evaluate the quality of the teaching material. Third, during teaching, the teacher can receive feedback from diverse students who might be of varying ability levels and knowledge backgrounds, and these feedbacks will offer value information for the teacher. From these feedbacks, the teacher might be able to recognize ignored gaps in the teaching material and even in its own knowledge, and also discover the teacher might be able to discover novel connections. Now we have know how and why LBT helps human learning. In this NeurIPS work, we explore can LLMs also learn by teaching for better reasoning. We implement LBT idea for LLMs as three methods, focusing on the potential benefit B and C of LBT mentioned in the previous two slides. In the future, maybe implanting the benefit A, improving the incentives or motivation into the LLM learning process is also worth trial. We note that LBT has the potential to improve stronger model by having them teach weaker ones, which is a form of weak to strong generalization, which this term has been recently discussed in the field. This might offer opportunities for continuous model evolution, especially as we are now facing the data scaling challenges. Here is an overview of our three methods. First, borrowing from the benefit B, our method 1 and method 2 implement LBT as a rationale or answer scoring method in the well-established search-based output generation pipeline or the generation scoring fine-tuning pipelines. This scoring method uses the student's performance to score one rationale and answer of the teacher. Borrowing from benefit C, our method 3 implements LBT as an iterative prompt tuning process or prompt optimization process. In this process, the teacher analyzes the students' failure cases and improves the prompt for the teacher itself. I want to note here that the introduction section in our paper has introduced these three methods from a perspective of building a procedure analogy between our three methods and the teaching procedures in human learning. That is, we categorize a teaching procedure to belong to three levels. L1, level 1, is that the teacher instructs the students and only observes the students' feedback as an indicator of the quality of the teaching material. And level 2, or L2, is that the teacher can improve its own knowledge based on the student's feedback, which we call learning from the feedback. And level 3, L3, is that the teacher teach the student, observe the feedback, and learn from the feedback in an iterative way. So from this perspective, we can see that our method 1, method 2, and 3 are analogous to these three LBT levels, L1, L2, and L3. Here is a results summary of our three methods, and we conduct experiments on mathematical reasoning, competition level code synthesis, and as well as some verbal logic reasoning tasks. And we can observe some improvements using our three methods. We will go into the detailed numbers in the following slides. So in the next section, I will go through the detailed method design and the results. In the level 1 procedure, the teacher instructs the students, who then provide feedback. The student will take exam, and the student exam score can be used as an indicator of the quality of the teaching material. Note that this procedure is based on the LBT assumption we have mentioned before. Let me repeat it here. The LBT-TMQ assumption goes like this. Teaching materials that make it easier for the students to learn have clearer and more accurate logic. So accordingly, the idea of method 1 is that for a given teaching problem, we generate a set of rationales and answers, and then we score each rationale and answer pair based on its ability to teach student models to correctly answer other similar problems. We hope this LBT score can help select better answer for the given teaching problem and achieve a higher answer accuracy for the teacher. So there are 4 key implementation choices in this method. The first one is, what is the form of the teaching material? In our work, we let the teacher generate a teaching rationale and answer, abbreviated as TR and TA, for the teaching problem as the teaching material. The second question is, how do the students learn from the teaching material? In our work, for simplicity, we use in-context learning to let the student learn from the given teaching problem, teaching rationale, and teaching answer example, instead of some backpropagation-based method. The third question is how to evaluate the student's learning performance. We'll let the student model to take an exam to solve some exam problems, and these exam problems are similar to the teaching problem, and then the students will get an exam score. The final question is that how do we utilize the feedback of the student, which is its learning performance or its exam score? We call the exam score of the students as the LBT score of the teaching material, which is teaching rationale and teaching answer pair. And the teacher will generate multiple TR and TA pairs, and we will select the teaching answer with the highest LBT score. This method, we will call it method 1 max. And another variant of our method 1 is method 1 sum. This method uses weighted voting to decide the final teaching answer, and then we hope the decided teaching answer to have higher accuracy. Okay, to be more specific, Firstly, we let the teacher LM generate multiple TR and TA pairs for a given teaching problem TP. And then each TR and TA pair will be separately used as the in-context learning example to guide a student LM to solve various exam problems and get the exam rationales and answers. With the produced exam rationale and answers, each student will then receive an exam score, denoted as LBT score. And the LBT score can be used as a quality assessment of the corresponding teaching material, which is the TR and TA pair. Finally, we consider two ways to select the final teaching answer. Method 1 max selects the TR-TA pair with the highest LBT score, which is shown in the figure, because the third sample of teaching rationale and teaching answer has an highest LBT score of 1.0. So method 1 max finally select the answer of the sample 3 as the final teaching answer. Another variant is method 1 sum. For datasets whose answer equivalence can be decided relatively easily via exact matching, for example, as in the math dataset, we can take the sum of the LBT score for each individual choice of teaching answer separately, and we will select the teaching answer with the maximum sum of the score. Okay, then I'll go through the evaluation of method 1 on mathematical reasoning and code synthesis. For mathematical reasoning, we use the functional math dataset. This dataset is an extension of the math dataset, which is very widely used. In the Let's Verify step-by-step paper, the paper split the math dataset into a train test split that contains 12,000 training problems and 500 test problems. We respect this split. Among the 500 test problems in this train test split, the functional math has provided 3 functional variant problems for 181 problems in the 500 out of the 500 test problems. The functional variant problems have the same problem structure and solving strategy with the original test problem, and only differ in the values. So we used 181 out of 500 test problems that have functional variants in the functional math dataset as the teaching problems. And for each teaching problem, we generate 256 TR-TA pairs. And then for each TP, we utilize the 3 functional variants of the teaching problem, TP, as the exam problems. And then for each exam problem, we answer the exam problem with the student LM 3 times with randomized decoding. Finally, there will be 9 EP-ER-EA pairs in total for scoring 1 TR-TA pair. Okay, that's all for the setup for M1 on mathematical reasoning. And then for the results, first we can see that method 1 is effective with various model settings and surpasses baselines. We mainly use the self-consistency as a baseline, and also in the appendix of our paper, we use self-evaluation as a baseline too. And method 1 can benefit from teaching multiple students. As can be seen, using GPT 3.5 to teach both Number 3 8 billion and Mixture 7 billion together will achieve an improvement over teaching Llama 3 8 billion and Mixture separately. In the previous comparison, all methods including the self-consistency baseline, and our method 1 use 256 TRTA pairs. Under that setting, actually method 1 incurs higher inference cost than self-consistency because it involves the inference of the student LLMs to calculate the LBT score. So to conduct a comparison with comparable and or much lower compute, we can see that with comparable and much low compute, our method 1 with just 24 TRTA pairs can still achieve an accuracy improvement over self-consistency with 256 TRTA pairs. From the left figure, we can see that the relative improvement of method 1 over self-consistency will increases as the number of TRTA pairs increase. And it seems that the improvement does not saturate at the number of 256 TRTA pairs. From the right figure, we can see that LBT is much better than self-consistency on harder problems. Intuitively, this is because method 1 can identify infrequent but correct teaching answers. In contrast, self-consistency requires a correct answer to be in the majority of all the answers to derive the correct one. Note that the teaching problem and the corresponding exam problems need to be similar for the LBT score to be indicative of the quality of the teaching rationale and answer. Actually, this is intuitive and expected. So that's why we use the functional variants of each TP as the exam problems. We conduct an early application study that selects exam problems from the original math training set instead of using the functional variants. We specifically we select 2 closest problems to the TP according to a semantic sentence embedding model as the exam problems for this TP. So to visualize this experiment, we sort the TP by the cosine distance to its corresponding EPs and calculate the relative improvements over SC on each fraction of TPs. So as shown in the figure, our method 1 only provides improvements for teaching problems that have very similar problems in the training set, but cannot provide improvement and even result in a slight accuracy decrease when there are no similar exam problems for this TP. For the evaluation on the competition level code synthesis task, since as we already know, for the LBT scoring to work well, we need the teaching problems and the exam problems to be similar. So we fetch multiple problem groups or data sets from the Grandmaster Dynamic Programming Study Plan on code. Each problem group or data set in the study plan has 5 to 10 problems, and each problem has 2 to 3 visible test cases that are available, and many hidden test cases. In order to get the score on the hidden test cases, we must submit the code to the LeetCode platform. So we denote the score on the visible cases as the visible score or V-score, and denote the score on the hidden cases as the submit score or S-score. Note that we calculate the exam V-score as the LBT score instead of the exam S-score because we want to avoid additional LeetCode submissions when we calculate the LBT score. To be more specific, we use 18 problems in 3 datasets, including game theory, bit masking, general 1D as the teaching problems. And for each TP, we generate 8 TRTA pairs. In the code synthesis task, the teaching rationale will be a natural language rationale, and the teaching answer will be a Python code. Then for each TP, we use other problems in the same data set with the TP as the EPs. So there will be n-1 exam problems for the TP. And for each EP, we use greedy decoding to let the student LM to generate only one ER-EA pair for this EP. So finally, there will be n-1 EP ER-EA pairs in total for scoring one TRTA. So let's go through some of the experiment results. First, method 1 can select better TRTA than the baseline in most cases, which we have already marked in green. Note that here the baseline is the average submission score of all TR and TA pairs, or the average submission score of the TR-TA pairs whose V-score equals 1. That is, it was 100% correct on the visible cases. Another message is that method 1 shows the largest improvement on the teaching problems with medium difficulty. For very simple cases, for example, when we run GPT 3.5 or Llama 3 70 billion on the SG4 problem, this problem is too easy for these models, so we cannot expect our method 1 to further improve the accuracy. And for very challenging cases, for example, except this GPT 3.5 with self-debugging technique, in all other cases, the SG2 problem is very challenging. And in this case, maybe there is no correct answer among the 8 teaching rationale and teaching answer pair. So except for this case, M1 cannot achieve significant improvement on SG2. We have mentioned that we have incorporated the self-debugging technique with method 1. And the message is that self-debugging is both complementary to and beneficial for method 1. Self-debugging usually fixes simple non-logical bugs such as missing imports, miswritten variable names, and so on. So we see self-debugging is complementary to M1 since self-debugging fixes non-logical bugs, while our method 1 mainly assesses the quality of the logic. So if we apply self-debugging on the teaching answers, the effect of self-debugging and our method 1 will be complementary. On the other hand, we see that applying self-debugging on the exam answers is beneficial for method 1 itself, as fixing the non-logical bugs in the exam answers can make the exam score more indicative of the quality of the teaching rationales and teaching answers logic. So we can see that after applying the 1 iteration self-debugging technique on both the baseline and method 1 will show consistent improvement on all the problems. Let me wrap up the discussion of method 1 by revisiting method 1 in the context of literature. Many existing prompting pipelines for improving LM reasoning can be summarized into a search-based output generation pipeline. It contains a sampler that keeps a search history of the rationale steps or chains, and also in charge of sampling new rationale chain or steps. The second component is an evaluator that can evaluate the quality of each rationale chain or step, and the evaluation score will guide the sampler to do the search. Finally, a final deriving step will derive the final rationale or answer from the search history. Again, our method 1 is proposing a new scoring method or new evaluator for scoring one rationale and answer. Although we implement a simple pipeline which is actually a weighted self-consistency method, a weighted voting, or selecting the answer with the highest LBT score. Our scoring method can actually be extended and used as the evaluator in other general search-based output generation method. So a related work, NiCS-EffAlg, can actually be considered as an implementation of LBT scoring. NiCS-EffAlg evaluates each partial rationale by measuring how often another completer model arrives at the correct answer by continuing from the partial rationale. In NiCS-EffAlg, the students are examined by extending the partial teaching rationale for the same problem, whereas in our method 1, typo, the students are examined on similar problems, using the full rationale from the teaching problem as an exemplar. So we just hope that framing this NiCS-EffAlg method together with our method within the LBT framework could help make the roadmap for drawing insights from human education more clear. That's all for method 1. Then we conduct a relatively small-scale experiment that further fine-tunes the teacher LLM to make it better at reasoning, leveraging the students' exam scores. Specifically, we use exactly the same LBT scoring method in method 1 to score the teaching rationales. And with these rationale score pairs, we then apply direct preference optimization, DPO, to fine-tune the teacher LLM with these pairs. So we show that the LLM tuned by method 2 is better than the LLM tuned using DPO, but only with the teaching answer correctness as the score of the teaching rationale. The left figure shows the baseline method, which uses the correctness of the teaching answer as a score of the teaching rationale, TR, that is 0 or 1. So then use DPO to train on the rationale and score pairs. So this scoring method cannot reflect which teaching rationale is best among multiple teaching rationales that are all correct or incorrect. We use 1,564 math training problems that have functional variance in the functional math dataset. And after fine-tuning the model, we tested the fine-tuned model on the 500 math test problems. For each TP, we sample 32 TRTA pairs from the teacher and use the 3 functional variants of the TP in the functional math dataset as the exam problems. For each TR, we calculate 0.5 times the teaching answer correctness plus 0.5 times LBT score as the score of this teaching rationale. Well, the correctness is 1 or 0 when the teaching answer is correct or wrong, respectively. And we select pairs from the 32 teaching rationales whose score difference exceeds a threshold of 0.3 and keep at most 8 preference pairs for each TP. Due to the large compute cost, this experiment is not so thorough and large scale. We only observe preliminary and slight positive results. We show 2 examples in our paper where LBT scoring can discern preference between TR and TA pairs. In which, for example, one example demonstrates that although the 2 TRs produces a correct TA, but the losing TR actually is unnecessarily verbose and cannot be generalized to other similar problems. Putting method 2 in the literature, what method 2 is doing is just incorporating the LBT scoring method into the generation scoring fine-tuning pipeline. This pipeline can be summarized as 3 steps and contain a lot of training-based methods to improve LLM reasoning. The first step, let the target LLM or teach LLM to generate multiple rationales for a given problem. The second scoring step, score the rationales. And the third fine-tuning step, fine-tune the target LLM using the scoring results by reinforcement learning, by DPO, or by filtering and supervised fine-tuning, or by score conditional SFT, and so on. So our method 2 chooses DPO as the fine-tuning method and LBT-based scoring as a scoring method. So it's just another implementation of this generation scoring fine-tuning pipeline. Let's go into method 3 here. Method 3 corresponds to the level 3 of LBT, that is learning from the feedback iteratively. From the feedback form dimension, instead of leveraging the student's exam scores, method 3 leverages the student's detailed exam response to help the teacher iteratively refine its own prompts. And from the LBT implementation or an analogous benefit perspective, instead of implementing the LBT teaching material quality assumption as a scoring mechanism, as we have already done in method 1 and method 2, our method 3 implements the LBT benefit C as an iterative prompt tuning process. Specifically, we guide the teacher to iteratively improve teaching material in the form of a set of exemplars based on the student and teacher performance when the set is used as the ICL examples. The final set of exemplars is used as an ICL example to test the teacher's performance on a holdout test set. To be more specific, firstly, given a task, we sample some exemplars and use them as an ICL example of the student to answer the exam problems. Second, we will run multiple refinement iterations to refine the prompt or the exemplars. In each iteration, the current exemplars are used as the ICL examples to teach students to answer exam problems. And then, we will select the exam problems that teacher answered incorrectly and prompt the teacher to analyze why the current exemplars might have misled the students in these instances. Based on the reflection, we ask the teacher LM to generate multiple updated exemplar sets, and we will keep the exemplar set that achieves the best teacher performance. Finally, we will report the teacher performance on a holdout test set when using the resulting ICL examples. This is the experiment setups. For data sets, we use 2 verbal logical reasoning dataset, liar and logical fallacy. We cast these 2 tasks as a binary classification task. For more implementation details, we maintain 4 exemplar sets, and each exemplar set contains 8 positive or negative exemplars. Here, positive means class equals 1, and negative means class equals 0, as we already cast the task as a binary classification task. And we run a total of 5 iterations of teaching material improvement. For each current exemplar set, the teacher will generate 8 new exemplar sets by analyzing the students' values. And out of the 4 times 8 equals 32 new sets, we will choose the 4 exemplar set with the highest F1 score on the training set, tested with the teacher LM, and to keep it as the exemplar set in this current iteration. Finally, after the 5 iterations, we will report the teacher's F1 score on the dev and test split combined. We can see that the teacher LM is able to reflect on the failure cases of the students and propose revised exemplars that can improve the teacher's performance. As the iterations go on, we can see the teacher performance are improving. Also, we can see that having 1 or multiple LMs different to the teacher as the student improves the quality of the teaching material faster. We speculate that this benefit might be due to the more diverse error types made by a different student model. In our appendix, we have a detailed interpretation results to verify that by choosing a student model different from the teacher model, we can identify more types of valid causes of the teaching mistakes, and LBT actually can help solve these errors. Okay, then I'll go into some discussions. First, I want to share our insights into in-context learning. Some prior work has found that a correct input-output pairing in ICL example does not matter that much. However, we find that two key factors are very important for successful ICL following. And if the ICL following is successful, then the ICL example's correctness matters. So it will establish a positive correlation between the ICL example accuracy and the answer accuracy. The first factor is that we need to use chain of thought, or we need to use a detailed rationale. This will help ICL following. To quantify this, we define a measure called style follow rate. This measures whether the exam answer matches the coding style of the teaching answer. Okay, by the way, we only do this experiment on the code synthesis task. And from the results, we can see that provided the rationale in the ICL example will result in a higher style following rate. We define another measure, the in-context learning example ignore rate. This measures whether the exam answer style matches that of the code generated by the student without any ICL example. So if with the ICL example, you are generating roughly the same code as what you are generating when there is no ICL example, then the ICL example might be ignored, right? So we can see that provided the rationale in the ICL example will result in a much lower ICL ignore rate. Thanks to the successful ICL following, we can establish a positive correlation between the ICL example accuracy, which is the teaching answer accuracy, and the answer accuracy, which is the exam answer accuracy or the LBT score. Okay, here we introduce the second factor that is important for ICL following and this positive correlation, which is that the TP and the EP need to be similar. So we can see from this table, which is also in our appendix, that when the teaching problem and exam problems are similar and the teaching rationale is provided in the ICL example, the ranking correlation between the teaching answer accuracy and the exam answer accuracy will be higher, and we can select high accuracy teaching answers based on the submission score or the V score of the exam answers. Okay, for limitations, actually, our method 1 and method 2 has a very impractical property. And the most impractical thing of method 1 and method 2 is that it needs similar EPs and their GT answers to correctly score a rationale. And also we selected suitable EPs according to human-provided similarity information. For example, according to the manually grouped problem groups on LeetCode. There are some possible extension of method 1. For example, can we synthesize similar problems if there are no similar EPs or that is already available? And for the second problem, which is we need GT answers of these similar EPs, the first thought that comes to mind is that can we synthesize GT EP answers with the LLMs? Actually, we made some attempts, but not very successful. And the other thought is that actually we can let the teacher give a score of the exam rationale and exam answer, something like self-evaluation, instead of using the ground truth EP answers. And for the third one, instead of relying on human-provided similarity information between problems, maybe we can let a model to automatically identify similar EPs to a TP from a large pool. Okay, you can check our paper for more extension possibilities. I will not go into the detail here. And the second limitation is that we only experiment with problems with oracle ground truth answers or test cases. But in principle, LBT can be extended to open-ended problems, such as dialogue, writing, open-ended math problems. Maybe we can let the teacher evaluate the student's answer and provide LBT score, as we have just discussed. Also, in the peer review process, a helpful reviewer has suggested a very important concern is that our pipeline might have a potential risk of bias perpetuation. For example, in open-ended problem where no ground truth judgment exists, and we need to use LM-based judgment as we have discussed just now, it is possible that the teaching material that is well accepted by the students are actually not necessarily closer to the truth. Instead, they may align with the existing bias of the teachers or the students. This will pose a risk of the teacher that perpetuating their own biases or learning from the students' biases. Okay, for some future roadmap, we have summarized in our paper that we can borrow more education strategies to improve LLMs. As LLMs are showing some amazing abilities, maybe some educational strategies can be more helpful for the SOTA LLMs. We categorize into two types of borrowing. The first type is borrowing the design strategies of teaching materials. And the second type is borrowing the education pipelines to design new inference and training pipelines. We have given a few examples in our paper. And I will not go into the detail here. Okay, then we come to the summary. Our target is improve LM reasoning, which might be the bottleneck of the current LM. And our high-level idea is that we want to borrow from human learning. We want to borrow the learn by teach idea, which is very helpful in human learning. And we specifically we want to borrow from these two benefits. Benefit B is that LBT, the LBT idea can assess, suggests that we can assess the quality of the teaching material based on the student's performance. This is LBT TMQ assumption. And the other benefit is benefit C, is that the iterative feedback from diverse students can help identify ignored gaps in the teaching material or the teacher's own knowledge. Okay, and for the specific task, we choose mathematical reasoning, computational code synthesis, and verbal logical reasoning, because this task require accurate knowledge and reasoning and cannot be easily solved through vague logic or simple memorization. This is just relative to other tasks. Okay, then for the actual specific implementation, we implement method 1 and method 2, which actually implements an LBT-based scoring component, leveraging this LBT TMQ assumption. And we use this scoring component in well-established pipeline, like the search-based output generation or the generating, scoring, and fine-tuning pipelines. And in method 3, we implement an iterative teaching and feedback process for prompt tuning or prompt optimization. There are some findings and possible potentials of LBT. For example, M1 is actually a new way of scaling up inference compute to obtain accuracy benefits. And our results suggest that LBT has some potential for harnessing the diversity offered by different students and facilitating weak to strong generalization. Actually, I want to emphasize the contribution of our paper on a positioning role, because we have provide a roadmap of potential future research very carefully in our section 6 on how to borrowing educational concepts in improving LMs. And we have also provided a discussion on our research rationale during this project in our Appendix D. Yeah, I must say that our current method, especially method 1 and method 2, has its impractical aspects. But I think I want to convey some ideas and our thinking on how to further improve LM reasoning in our work. So I want to emphasize again on the positioning contribution of our work. Here again, I summarize some of the results. For method 1, we experiment with mathematical reasoning and code synthesis, and we can see that using the score provided by the LBT scoring method to select answer, we can select answer with better accuracy and code pass rate. Also in method 2, we use the score of the LBT scoring method to tune the LM with DPO, and we can further improve the LM's ability. And in method 3, we let the LM to analyze the students' failure cases and improve the prompt for the teacher itself. And we can see that method 3 can craft better ICL examples through multiple refinement rounds. Many thanks for the attention. Welcome to check our paper, code, and website of the group I'm currently leading. Feel free to email me for any discussion on this work or other collaboration focusing on LM reasoning. Thank you.